Hello, once again, AP Calculus students. Mr. Record here at Avon High School. We are talking about the chain rule, dealing with trig functions. We're here with my Period 2 class. Period 2 class, can we get a shout out? They're excited, you can tell, right? Okay, so we're talking chain rule with trig functions. And if you're watching the video, the thought process is that you've already exposed yourself to the basic derivatives of the 6 trig functions. And what you can see here on the screen is a slight adaptation, right? Maybe you guys were looking at another video, whether it was from me or your teacher in your class said something along the lines of, hey, the derivative of the sine of x with respect to x is the cosine of x. And that's exactly right. But if you think about that x as being something a little bit more meatier than an x, so we're going to call it a u. Maybe this thing is x squared, or maybe this thing is 2x, or maybe it's x divided by 3, or maybe it's like a theta, 5 theta, anything along those lines. That means that you've got something a little bit more substantial than just a plain old x, and therefore you're going to have to do the chain rule. And so you can see that you just need to multiply by the derivative of that particular expression. All right? And I'll use my charms blow pop analogy when we work the examples. So for example 7, it says find the derivative of each of the following trig functions. So our first one is the sine of 2 times x. Well, oftentimes with my students, in fact we did it just yesterday in here, we would write parentheses around the argument, around the expression that's embedded in the trig word. So we have the sine of the quantity 2 times x, basically. Because if you can put parentheses around things, then that means that you can identify this all-important u value. And that u value would be 2x. Now, depending on where you're watching this, you're probably thinking, what in the world is this picture all about? Well, there are a lot of teachers, maybe your teacher is one of them, that uses the analogy of a charms blow pop sucker, where you've got the outer candy shell, right, which is our outer function sine, and then the bubblegum center, which unfortunately you can't see, but let's pretend it's right in there. The bubblegum center is going to sort of act as the u value, the inside, okay? Some teachers use M&Ms. M&Ms is another good example. Right? M&Ms would be a lot cheaper. I could have probably brought in M&Ms and gave each one of you one single M&M. Thank you, Mr. Record. That's pretty cheap of you. But do you see what I'm talking about? How the candy shell would be the outside, and then the chocolate part would be the U or the inside. So if we continue with this problem, this gum that we found, this inside part, U equal 2x, can then join forces with the outside, which is the sine of u. And then we've learned that our chain rule, dy dx, which my students that are here with me today, you probably don't need to write this down because we've gone over this. But if you're watching this elsewhere, this is pretty much what you guys have learned about the chain rule. So you would just multiply these two parts together. So you could say that your final answer, dy du, well, that's the derivative of y with respect to u, which is the cosine of u. And then you'd multiply that by the derivative of u with respect to x, which says come over here and take this guy's derivative, which is 2. And then are we allowed to leave the answer like this, my class? No, we cannot. And the reason is because we don't like this, do we? We don't like that u in our answer. So it's a very simple thing to fix. You just back substitute the 2x that you had for your u value. And it's up to you if you want to put parentheses around it. You don't have to. To be quite honest, the 2 that you would have afterwards probably looks a little bit better in front. But as long as you have an equivalent expression that, you know, is void of any kind of mathematical notation that's incorrect, you would be fine. You would be fine. All right? Yep, Sean. I agree. Just like we talked about before, when you develop a certain level of proficiency, you will not have to show any work with these, nor would I expect it. And I think, teachers around the country would probably say the same thing to their students. We don't want you guys spending lots of time solving a question like that, take that derivative. We want that to be easy. And if that's the case, why don't we do something a little bit more efficient with our next two examples? So in this particular case, we identify the u as 3x minus 1, right? So if that's the situation, then for our derivative, isn't it very, very likely that we're going to have the derivative of 3x minus 1 as part of our answer? Why don't we put that down first? Basically, it's the derivative of the bubblegum center first. The derivative of the chocolate part of the plain M&M. Now, we look at the outer part. That's the derivative of the cosine function, which we know to be negative sine. Okay, now I feel bad. I probably should have saved a little bit of room for a negative that could go there. Now I've got it. And then the derivative of cosine would be the negative of the sine. And then we want to keep the 3x minus 1 intact. And that would be it. That would be the correct answer. Right. Now, does that sit well with everybody? You're okay? You can call that sort of a shortcut if you want. But you're essentially just doing all of this work mentally. All right. Let's take a look at the third and final one here, the derivative of the secant of 4x. What's a little tricky about this one? Well, the u is hopefully clearly going to be the 4 times x, which means the derivative is 4, right? So we'll start with our 4. But what is the derivative of the secant? It's secant of that value times the tangent, right? It's got 2 trig words to it. So that's okay. Just make sure that the 4x is the argument of both the secant and the tangent. And it looks like I'm getting a little bit cramped for space, so I'm just going to move some things over. And now all is good. Okay? Now, one common misconception is students think that they have to write this 4 twice, that it needs to be attached to both the secant and the tangent, and that's not true. It only is attached once. Question? Now you got to be careful, because when you say secant tangent, that doesn't make it. You have to have some kind of an argument after every trig word that you write. Does that make sense? So like secant tangent 4x, this is leaving the secant kind of hanging a little bit. Okay, good question. So, all right. So, yeah, go ahead. No, and that's a great question. The question was, do we ever have to simplify these with trig identities? Thank heavens, no. There's ways to do that. There's an adaptation of double angles with both of these, and we're not going to go there. Okay? It doesn't serve us any purpose at all. So, all right. All right. Now, the very last part about this trigonometric chain rule discussion. This is the tip of the iceberg, you guys. This is now trigonometric functions that might require a repeated use. So if the chain rule in trig is ever going to get difficult for us, this is where it's going to be, and this is as difficult as it will ever become. So if you've mastered this, you guys can pretty much take the derivative of any kind of trigonometric expression. Now, if you look at example 8, part A, do you see what's new about it? Do you see that not only is the trig word raised to a power, but we have an argument that's not just a plain old x. So the first thing that I'm going to suggest that students do with this is rewrite it so that the power is on the outside of the trig expression. And that's going to require a nested use of parentheses. You're going to have the 3x perhaps in parentheses. I put it in parentheses just to make it sort of stand out. But then the whole sign of 3x is being raised to the 4th. We talked about how this is the way that you would have to enter something like this into a graphing calculator, like the TI-84 or the TI-Inspire. Now let's go back to our charms blow pop analogy. Now we have something else going on. We have the bubblegum center, which is the 3x. We have the candy shell, which is the sine of 3x. And then we have this whole thing to the 4th power, which is the outside of the candy shell, which would be what? The wrapper. That would be the wrapper, right? If this was an M&M analogy, you tell me what kind of M&M are we talking about? A peanut M&M, right? Yeah, that's what we're talking about. The 3x would be the inside, which is the peanut. The sine of 3x would be the chocolate, and then the 4th power would be the hard shell. Okay, so however you want to think about it, it would work. For some of you, it's like these candy analogies don't do anything for me but make me mad because I'm hungry. Now I want candy. That's okay too. So how do we go about doing this? Well, let me show you. What you're going to do for this derivative is work from the outside in. So you're going to bring the 4 in front, keep the sine of 3x as he is. Don't rush him, just leave him as he is. And then the power of the sine of 3x would be to the 3rd, right? You've done your power rule. But that's not the correct answer for the derivative, right? We have more work to do. We now have to take the derivative of the inside, which is pretty much now the candy and the gum. So what is the derivative of the sine of 3x? Well, that would be the cosine of 3x, but we still have to continue because the gum needs a derivative, and the value of that derivative of 3x would be 3. So do you see the double chain rule? There's 2 links in the chain, so to speak. Okay? And of course, we could simplify this by multiplying the 4 and the 3 and get 12. And then whichever order you want to write your sine and cosine makes no difference. And if you want to put that 3 in its usual spot, feel free to do so. But that would indeed be the answer. And this is something that you could check with your calculator. Okay? Again, these just take practice. The more of these you do, the better you're going to feel. So if you look at B, B has all sorts of problems. It's not ready to take a derivative yet. So let's rewrite this so that it has a power attached. And we all know that raising something to the 1/2 power is equivalent to taking the square root and vice versa. So is everybody comfortable with that rewrite? Okay? Here we go. Derivative time. The derivative of y with respect to x would be, work from the outside first. You're talking about the wrapper of this charms blow pop. The 1/2 in front multiplied by the secant of x over 2, all raised to the negative 1/2. But don't just stop there. We've got all of this inner stuff that we now need to take the derivative of. So what is the derivative of the secant function? That would be the secant times the tangent. Notice how the x over 2 just stayed as he was. And then what's the final thing that I would multiply by? What is the derivative of now this inner function? 1/2. And I'll write that, say, in green. Okay? And, you know, we're essentially finished. This is in good shape. It's not very well simplified. I'm going to suggest that we do that. And the way that we could simplify this would be, let's write this in purple, is note that we've got a pair of 2's that are in the denominator. So I could just start off with a 4 down there, right? Now, it looks like I might have some other things down there, but I might not. If I don't, then 4 is my only denominator. I can center the 4 later on. And I think that's what's going to happen because this guy here with the negative exponent's not necessarily going to drop down below and really stay there because what do these two combine to make? Can I see? A secant to the negative half times the same secant to the first is a secant to the positive half. Am I right? So you have the square root of secant up on top. So that's what we're going to put, the square root of secant, but I'm also going to have the tangent join him, and I can choose to write them in whatever order I want. I like to put the square roots sort of at the end so I don't get confused by what's under the square root symbol or not. And then the 4 is the only thing that I have in the bottom, which means I can just scoot it over. I know you guys would have to erase it and rewrite it if you wanted to, but that would be our final answer. Okay? Last one more. For part C, we're going to go ahead and do our rewrite. And the rewrite doesn't have much going on with it because the power 2/3 already there just needs to be written around the outside. Okay? Now let's take our derivative. dy dx equals. We do our outside derivative first, place the 2/3 in front, take our cotangent of 3x over 2, but then we have to consider what is the new power that we are raising that to. Once we subtract 1 from 2/3, we get negative 1/3. All right, keep pushing on. What was the inner part of the function? The cotangent of this quantity. What is the derivative of the cotangent? That's a trickier one, right? Is it negative cosecant squared of that quantity? And then the last piece, multiply by the derivative of this quantity, which is 3 over 2. What do you think? Double chain rule. And then once we put it all together, we have some nice things happen. The 3's and the 2's cancel. Wow, that worked out really well. And really, guys, the only thing I would say to do would be to leave your negative cosecant squared on top. And then this cotangent to the negative 1/3 could drop below and be, say, the cubed root of cotangent. Are there other ways to write this? Of course, there are many, many ways to write these. But I think what you're looking at is if we were to see something as difficult as this on a multiple choice item, and I'm going to be honest, on the AP exam, it typically doesn't get this bad. On the AP exam, they're going to stick with sines and cosines, with powers, and maybe some argument like that. That's kind of the difficulty level in the exam. So, okay? Question? Yeah, on the free response, you guys can put your exponents out on the outside, or you can put them nestled within, and they're correct either way. So, good. All right. I think that takes care of us for our trig derivatives, functions that require repeated use of the chain rule, and ones that just could be tackled in one particular chain rule. Hopefully the video helped, and we will see you next time.